I'm going to talk about 4 projects today these are all part of a proposal that we submitted to USDA NEFA a few years back and that was funded. So the focus is advancing precision agriculture and site-specific irrigation management in California, in Southern California agriculture region. So these are just my team members that I would like to acknowledge their important role and effort in this project. 3 graduate students, Anish, Zahra, and Mohit, and Akanksha, my postdoc, who worked on this project. So this is a little bit information about the region that we worked on in this region. It's close to the US-Mexico border. That's getting water mainly from Colorado River, imported water. So the rainfall is close to 0. That is why irrigation management and water management is critical in the region. There is also, the agricultural region is close to Salton Sea, which has been shrinking and has caused environmental and health issues in the surrounding area. So it's really a system level issue or system level issues and problems that scientists from different disciplines are dealing with right now, and climate change, of course, added more complexity to this system. So agricultural areas that are mainly irrigated using surface irrigation system. So, and the runoff goes to Salton Sea. So both water quantity and quality and runoff from agricultural fields impact the chemical loads in the Salton Sea. What we did, we developed 2 tools, and then also we did a few other computer modeling. So the first tool that I'm going to talk about today is what we call SAM's desert. And it's basically a satellite-based agricultural management zoning tool for the desert agricultural region in Southern California. So if you're familiar with site-specific irrigation management, or in general variable application of inputs, so that's basically has been the main promise of precision agriculture. So in traditional agriculture, we apply inputs uniformly in the field, so we ignore the within field variabilities. But in precision agriculture, given the advances in the technology to collect site-specific data, we move towards a variable rate application of inputs by dividing fields into management zones, which are basically sub areas in the field that require same inputs. And that helps to optimize input, so or basically minimize the input and put the exact amount of input, water, fertilizer, or other types of inputs that needed based on the soil and landscape characteristics. So the main task, or the first important task to move towards variable application of inputs and variable irrigation, is to delineate management zones. But that requires site-specific data that may or may not be available in all the fields. A proxy or an alternative approach is to use remote sensing data and satellite images. There is evidence in the literature that satellite data would be useful to delineate management zones. But most of the tools that are available for zone delineations are usually sophisticated, not easy to implement, or not freely available. So that was the motivation behind this study. We wanted to develop a tool that is easy to use for growers. So basically, as easy as they just go find their field, click on their field, and they see the zone. So the multiple questions are here that should be answered. First, how many zones are the optimum number of zones in my field? Where those optimum number of zones are located? And what input to use for zoning? So we decided to use NDVI, which is basically a crop index that has been used for decades now for agriculture all purposes, and it's highly correlated to crop health, and people usually understand it. So the higher number usually indicates less stress and vigor and greener crops. So we use NDVI. We got satellite data from Landsat 8, which is freely available, and there are a lot of moving parts behind the scene, but we don't want to make a complex tool. So everything is happening behind the scene. We actually pre-generated all the results for all the fields in the region. So you can see this is the dashboard of the tool. It's a remote sensing or a GIS-based tool. When growers find their fields and click on a specific field, what the tool does, it generates some results. First, what is the range of NDVI in that field? How many zones we recommend as the optimum number of zones? What is the map of optimum number of zones? And then a graph that we call it performance graph. This is basically showing how much of a variability you can explain as you start delineating more zones. So it's the typical curve that you would expect to see is that as you start adding more zones, your ability to explain variability would increase, of course. This is what you expect to see, but at some point it levels off, and after that you don't really want to have too many zones because it makes the at least for irrigation, it makes the irrigation decision making very complex. So there are some mathematical equations and calculations that goes behind this, but we basically generate this graph for all the fields that shows, for example, this particular field, one zone or no zoning, basically uniform application. You can see when you delineate 2, 3, and 4, and then after that, when the variability explained is less than 10%, we call it the optimum number of zone, or no further zoning is required. So this tool is already launched, so the growers can use and professionals can use it. And I'm going to show some results of also a detailed special analysis that we did on top of this tool, and all of these are actually recently published. I'm going to show you the paper too. So one thing that we notice is that if you look at the literature in zoning and zone delineations, usually researchers focus on 1, 2, or 3, or 4 fields. So they don't go beyond that. But there are questions that should be answered at regional level. So if we want to know what is the basically potential benefit of variable rate irrigation in Southern California or any other region, we need to do a regional assessment, which could be really complex, because we are talking about multiple thousand fields, and I think this is the first study that we did that, and the framework could be applied in other regions. So this map shows basically how many management zones we recommend in this region. So around 50% of the fields, we categorize them as in fields that are not variable. And this is based on the scene, April 27, 2018, that was the best Landsat scene that we selected to develop this tool. So these are the fields that, at least for this scene, they didn't show substantial variability. Half of the fields showed substantial variability, and from that 50% or half of the fields in the region, around 40%, they required only 4 zones, and the 11% 3 zones. So the take-home message here is that we don't really need too many zones to explain NDVI variability, and only 1% of the actually fields required 5 zones. Another question that we wanted to answer was about the accuracy of Landsat images. We know that they are freely available. They just launched Landsat 9. So it's a really good candidate to develop tools like these open access tools, but the resolution of the data is not that high. We're talking about 30 meter by 30 meter. So we wanted to know whether we are actually, the zones that we delineate using Landsat would be similar to a commercial product with much higher resolution. So what we did, we look at PlanetScope, which is commercial satellites that are so many of them that PlanetScope Lab that I think provide data, daily data for the entire everywhere, basically globe. And it's 3 meter by 3 meter, so basically 10 times high resolution. So we selected 5 fields with varying degrees of NDVI variability, and then you can see that this is field 1, 2, just for visual comparison. I put these maps here so you can see that Landsat zones left-hand side are very similar to right-hand side, which are PlanetScope zones. So we felt confident that the zones that were delineated using Landsat are at least a good start point for someone who is interested in exploring variable rate irrigation or fertilizer application scenarios. Another question that we had was about the variability over time. This is also something that is very important, both in terms of management zone delineation and also overall. If a field shows variability in one scene or 1 month, and then it doesn't show substantial variability for the rest of the year, maybe it's not really a good candidate for variable rate irrigation. So we look at 3 years worth of data, 2018, 2019, 2020, all the cloud-free images. And our criteria was that the fields that had at least in 50% of the scenes showed variability, that we could address it. So there are clustered variability, not random variability in the field. In NDVI, we consider them as fields that are good candidate for variable rate technologies. So our analysis showed that in this region, at least 13% of the fields actually may benefit from variable rate technologies. These are the fields that consistently show high within field variability that could be addressed by zoning. Another question that we had was that whether we could recommend dynamic zoning or static zoning. In practice, people usually do a static zoning, which means that they delineate zones, they change them over time. But our analysis showed that zones over time are not highly correlated, or in other words, we may need to change the zones based on the changes in crop properties. So dynamic zoning might be the better option for most of the fields. And this is the paper that basically put all the tools and everything and all the special analysis here just published, and it's open access. So I'm switching gears here to the second tool that we developed. We haven't launched the tool or deployed the tool. Is actually accessible now on my website. So this one is also for irrigation management for Southern California desert region. And this works based on the concept of water production functions. So this is a slide the graph that I borrowed from my former colleague, Daryl Martin at University of Nebraska, Lincoln. So beautifully explains this concept. If you graph applied water against yield for most of the crops, these row crops that I'm familiar with, you would expect to see something like this, a curved linear relationship. What this curve tells us is that you apply more water, of course, you have more yield. If you are living in a situation that you have rain-fed agriculture is possible, which is not the case for us, you have some yield if you don't irrigate, but then you have increase in yield linearly and then diminishing return, and eventually you get to a point that you apply more water, you don't see increase in yield, and for some crops even you may see some reduction in yield, like cotton, that may see excessive vegetative growth. So this is the concept that we grabbed. We wanted to develop a tool that growers can use to give them some ideas for water management, how much yield reduction they would see for major crops in the region if they practice deficit irrigation, and then combine it with some salinity management recommendations. And then, of course, if you plot ET or evapotranspiration against yield, instead of getting a curved linear relationship, the blue line here, you would get a green line. So the difference between the green and blue is basically what we consider non-ET loss. So you have runoff, deep percolation. So irrigation, the closer these lines are, the more efficient irrigation system and irrigation management is basically. So this is just a snapshot of the tool. There are 2 parts. The first part is simple and gives crop-specific irrigation recommendations. So again, when we designed these tools, we wanted to develop them for growers so they can easily implement them. They just need to select the crop, irrigation water salinity, what is the soil texture, and there is actually a lookup soil map that they can click and find the texture for their field. What is the irrigation system? What is the irrigation efficiency? If they don't have it, we have default data for each irrigation system. And then we give them some recommendations in terms of, okay, this is the evapotranspiration to maximize yield for the region. What is the irrigation efficiency? You need to add how much water to take that into account, leaching requirement, and the total applied water. And then another graph to show for deficit irrigation, how much yield reduction you expect to see if you basically start imposing deficit irrigation. And I need to mention this here that the data is coming from FAO. So when we started this project, we wanted to do it based on local data, but we soon realized that we don't have enough research-based information. So what we did, we grabbed FAO data that people use around the world, but then we revised them to make them more realistic for our region through consultation with extension folks who are working actually in this region. And then leaching requirements are calculated using two models, and then both of the models, the data are available. So that's basically the simple part. The more advanced or sophisticated part, if you will, is a part that we give growers the ability to compare water requirements of the crops to do a little bit of very simple optimization. So they can go up, select up to 5 crops first, how much water they have. So the assumption here is that I'm a new grower, I'm considering rotating crops or switching to another crop. So even a researcher wants to know the water requirement for multiple crops and compare them. So what is the water that you have? What is the irrigation system, water salinity and the irrigation system, irrigation efficiency? And then they can select up to 5 crops. This is the part that they can basically enter the site-specific data, because these data may not be 100% accurate for all situations. So if they know what is the maximum yield and what is the ET to get that maximum yield, they can enter it, and then we basically adjust the water production function care for that based on the data they entered. And we're also doing a very simple economic analysis. What is the crop price and what is the production cost? If they input no data here, we get the crop price from, I think, USDA report, and then also production cost is assumed to be 20% of the crop price. And then they have 3 options here. They can compare yield between the crops, and we generate some messages, whether they are practicing deficit irrigation, maybe they are over irrigating, they can conserve water, they can compare profit, and they can compare water saving potential. So we are still finalizing this tool, and we are, my student is working on deployment of the tool. The third project is also kind of related to irrigation, but it's mainly basically to generate yield maps that can be used for irrigation and other purposes. So there are, in California especially, there are crops that we don't have yield monitoring system, like cotton or corn. So growers don't have yield maps. And then we use yield maps a lot for variable rate application of inputs and other purposes. So since yield maps are not available, then we decided to work on drone-based imagery to see if we can use drones to predict yields for major crops. So we started with alfalfa, which is a major crop, but then we are also thinking to basically expand this work. So 4 fields hand harvested yield, and then we got drone data using this drone that has a thermal camera and multispectral camera. We haven't analyzed the thermal data, but I'm going to show you the multispectral data. So, and the models that we developed are very simple. These are just equations, so not very easy to implement. So the idea was that if I'm a grower or crop consultant who is servicing the grower, we have a map of these multispectral cameras. You can easily use our models to convert them to yield maps. All right, so these are just showing the performance of the models. Don't worry about different plots. These are different models. All of them are regression equations, just different inputs. I'm going to just pick one, maybe this one. D is multiple linear regression. We are using multiple crop indices. All of those crop indices are coming from the same multispectral camera mounted on the drone. These color-coded points are from different fields. The closer these points are to this one by one line, the higher is the accuracy of the model. You can see that the points are beautifully separated, which means that the model was able to differentiate between fields that had lower and higher yield. So, and then there were a few other things that we learned from this modeling work. And then first, again, the models were accurate to estimate yield variability between the fields, but we realized that they were not that accurate to estimate within field variabilities. We attribute that to the type of fields that data set that we had, because these fields didn't have substantial variability. We also realized that the closer is the actual drone data collection to harvest, the model performance would be higher. So in other words, there is a limitation in terms of early estimations. You cannot really fly a drone very early stages and expect that to be highly correlated to your yield. So I know I have 3 or 4 more minutes left, and this is the last project that I'm going to talk about. And my student Zahra is working on this one. So this is coming actually from an idea that I had when I was, ever since I was student myself in Tennessee. So in my opinion, the technology is ahead of us when we think about precision agriculture and variable rate irrigation. So it has been around for a number of years, but we don't have enough science-based data to really show the strength and limitations of these systems. And unless the scientific community can generate data and show their limitations, and their adoption rate would be low because of the price tag. So, and we know also there is limitation in terms of doing actual field work, and the number of scenarios that you can have are endless in terms of variabilities, different soil types, topography, shallow frangipane. I listed some of them here. So that is why we wanted to do some modeling to develop some information that hopefully could help researchers and ag community in general to understand how these systems perform. We picked Hydrus, which is a model that people use around the world. This is basically a model that shows water movement in the vadose zone for us, in the root zone and beyond the root zone. So when we have a field that is variable, if we have variable rate irrigation as opposed to uniform irrigation, what's going to happen? How much reduction in runoff we can see, how much reduction in deep percolation, and then we are thinking to actually couple this with a yield growth model to actually see the impact on crop yield. So again, the idea is that we come up with these hypothetical fields, run the scenarios, and then get some results to see where is the benefit, when can we actually, when we expect to see some significant water saving from these systems, when they actually are not that useful. So I don't have any result to share about this project, just wanted to let you know about it. We just started this a few months back. We are still running scenarios, and hopefully sometime soon we can publish something. So everything that I discussed here are related to models. I consider myself a researcher that mainly works on field-based projects, but still I'm aware of the limitations of the model. So when I talk to growers, I tell them that at the end of the day, you need to really understand your fields, and then know that models may or may not be accurate. So you need to look at the results always, have a knowledge about the variability, look at the results, assess them, and don't accept them without your judgment and your knowledge. So that's, again, these are all projects that were funded by USDA NIFA, and I would be happy to answer any questions that you might have.